Let's talk about bitwise operators. We showed you a little glimpse of this in the previous lecture when we talked about assignment operators, because assignment operators have all these compound assignments where you can perform an operation like an addition and then also assign. You can do the same things with these type of operators. But let's go into these in more detail and exactly tell you what they are. So C offers bitwise logical operators and shift operators. Those terms might be completely clueless on. They look like logical operators, but they're quite different. They don't do any kind of Boolean evaluations. They don't evaluate to true or false. They're not. They kind of look like the ampersand, the two ors, but they're not doing any kind of Boolean evaluation. What they're doing is they're operating on bits inside integer values. And so you may ask yourself, why the heck would you ever want to do this? Well, it's not used in most programs. It's more of an advanced technique. Even though this is a beginner class, they are part of the operators, and operators are a beginner concept. So I'm going to address them, but we're going to not necessarily focus on them a ton. I'll give you some examples, show you how you can use them, but you're not going to be an expert in this after this lecture. But the way that they're useful and why you'd actually want to use them is because you can store quite a bit of data. So there's bitwise operands called and, ampersand, and the bitwise or, which is an or, just a single parallel bar. Try not to get these confused again with the logical operators. The logical operators have two of them, ampersand, ampersand, which is an and. The bitwise operators just have a single, so just an ampersand or just an or. And so what they're going to do is they're going to test and they're going to set individual bits inside of an integer variable. What is a bit? Right? We know a bit is a way to measure data, but a bit is essentially just a 0 or 1 value. And 8 of those make up a byte, right? So a bit is a 0 or 1. And what you can do is an integer, remember, depending on the system you're running, could be 8 bytes. And so you could turn on and off each bit. And when I say turn on or off, I'm saying you can either have them be equal to 1 or 0. And then you can use those bits to tell you something. So you can store a lot of data by having bits represent some kind of data. And that's why one of the reasons why the computer uses bits and 1 and 0s and binary numbers to do operations, because you can store a lot of data. Now, exactly what this means is, here's an example, okay? You could use a single integer variable. Again, an integer is a number. An integer represents 4 to 8 bytes, depending on what system you're running. That means if there's 4 bytes, that means there's 32 bits. There's 32 zeros or 1 values. All right, so you can use all those bits to represent something. So for example, if you want to store individual characters of a person, you could just have 1 bit tell you whether or not the person is male or female by saying 1 is equal to male, 0 is equal to female. You just either turn it on or turn it off. Then you could use 3 bits to specify whether the person can speak French, German, or Italian. So the 1 bit could represent French. If it's not 1, 0, then that means they don't speak French. If German is 0, that means they don't speak German. If it's 1, it means they do speak German. So by turning off and on these bits, setting them 1 to 0, you can represent a lot of data. You could have another bit to record whether the person's salary is $50,000 or more. If it's 1, it's true. Yes, it is. 0, false. So basically, we just specified here, it actually says 4, but we actually specified 5 bits of data. Only 5 out of whether or not we have 32 or if we have 64 bits, but we only used 5, and we were able to represent whether or not a person is female or male, whether or not they speak French, German, or Italian, or all 3, or one or the other, and whether or not they're making more than $50,000. We can represent all that data in our bits. And these is where the bitwise operators come in handy. Okay, so the bitwise operators are summarized here. And again, another nice table I got online, but they look similar to logical operators, but again, don't confuse them. So the ampersand by itself is a binary AND operator. And so what this is doing is it's copying a bit to the result if it exists in both operands. So if both of them are true, then it's going to copy a bit. So if A and B is equal to 12, you're going to have a binary representation of 00001100. So A and B would be that number. And we'll go through some examples. A binary OR copies a bit if it exists in either operand. Okay, so A or B will copy a bit if it exists in either operand. So if either operand is equal to 1, it will copy a bit. And then the binary XOR, this is the exclusive OR. This will copy the bit if it is set in one operand but not both. So if you have a true but only one true, and you use the caret to represent this on your keyboard, then it's going to set, it's going to copy a bit and it's going to say it's true. Binary ones complement. So again, we're getting into binary data here because we're talking about bits. So hopefully one's complement operator is unary and has the effect of flipping the bits, basically just negating them, taking them on or off. So an example here was if you say tilde A, you're applying the ones complement operator. And if it's equal to negative 61, it will be 1100001, right? So if you were to actually convert that binary number to decimal, which is negative number, and the first number is the sign. So 1 tells you that it's a sign, and then you say 1, 2, 4, 8, 16, 33, 33, and then 61. So that's how it would be represented. So I'll go through more concrete examples of this, but basically, if you have a binary number, A is initially a binary number that's 00111100, which is 60, and you supply the flipping, basically, it's going to then turn into negative 61, which is 110000000011. Right? So these are the results of variables that are actually set. So if, again, I'm assuming that A has certain binary representation and B has a certain binary representation. So if A is equal to, again, 60 and B is equal to 13, then the result of ANDing them together, doing a bitwise AND, is going to be 00001100, which is 12. And again, I'll go through these examples, but this is trying to provide a little description of these different binary operators. The greater than symbol is going to, the less than symbol is going to shift bits to the left. So the left operand value is moved left by the number of bits specified by the right operand. So if you do something like A less than 2, and A is actually equal to, some binary number, for example, like 00111100, you're going to shift the bytes by 2. So you're going to take off the zeros and it's going to become 1111, and those zeros are going to go to the end. And the same with the right shift operator, you're just shifting them to the right as opposed to the left. Here you use the greater than symbols. And so I'm going to go through these in a second. The other important thing to understand with the bitwise operators is how do you evaluate these A and B values, right? So what does a 1 and a 1 evaluate to? A 1, if it's an ampersand. If it's an OR, 1 and a 1 evaluates to a 1 as well. But a 1 and a 0, if you're using an ampersand, doing an AND, that evaluates to 0, false, right? So I just wanted to provide a little truth table here that shows you the values when you do use an AND, an OR an exclusive OR. So here, if you have P0 and Q0, which means they're both false, and you apply an AND, it's going to be false because they both have to be true for that to be true. And that's what you see in row 3. If they're both true, then P and Q is going to be evaluated to 1, true. If they're not both true, it's always false. P or Q, only one of them needs to be true. So that's why you see rows 1 and rows 2 equal to 1 and row 3 equal to 1. The only time it's false is when they're both false. And then the exclusive OR is at least one of them is true and only one. Right? So if P is false and Q is true, it will return 1, true. And if P is true and Q is false, it will return 1. So this gives you an idea of how it's evaluated. Again, a lot of math stuff, but when we talk about binary digits, that's what we're talking about. So let's look at some examples, concrete examples in code blocks. Hopefully this will help a bit. Okay, so here's our main function. I'm going to create a couple for variables. I'm going to make sure that they're, they're unsigned, even though that's by default. Unsigned means what? Unsigned means they can be positive or negative. Right? Signed means they can only be positive. So if I say unsigned int A and assign it to 60, that's actually going to be represented in binary as 0011 and then 1100. If I create another unsigned variable and I say int B and I assign that the value of 13, that's going to actually be represented as in binary as 0, 0, 0, 0, 1, 1, 0, 1. You can do the conversions there. But what I want to demonstrate here is that when you set these binary numbers up, you can turn off the bits by using the different bitwise operands. Okay, so now then I'm going to just create a int result, and I'm going to say that's going to be equal to 0. He's going to hold the result of the bitwise operation. So now if I say C equals A and I apply the bitwise amperand and A and B, now what that should do is if A is equal to 1 and B is equal to 1, that bit's going to be turned on. Right? So what would you expect the result of this be? Well, you look at the first bit of A and you look at the first bit of B, and they're both 0. So the result is going to be 0, because if you do a true, an A and a B, they both have to be true in order to be 1. So the next one is also going to be 0. The next one is 1 and 0, the third bit. So that's still 0, 1 and 0, still 0. And then now we have a 1 and a 1. So now we finally have a true. We have another 1 and a 1. We have a true. And then 0 and 0 is going to be 0. And then a 0 and 1 is going to be 0. So the result, if I were to try to print out C, it's going to print out the value in decimal format. If I were to do something like that, the result is it's going to print out the decimal equivalent of that binary number, which would be the equivalent of 0, 0, 0, 0. And this is all converting binary to decimal, so you need to understand how to do that to understand this example. But 0, 0, 0, 0, 1, 1, 0, 0 is actually 1, 3, 7. That's the value is actually is 12. 1, 3, 6, 12. So this would print out 12. Right? If I were to print out C, or result would be better. So if I run this, you're going to see that the value is 12. It actually turned off and on all the bits based on the ampersand comparison. So now I say run, we see that the value is indeed 12. Because it's turning off and on the bits, and it's going to actually be represented as 0, 0, 0, 1, 1, 0, 0, which is the value 12, because we're printing out its decimal. If I were to change this, and I want to now do an OR, and I'm still doing the OR, and the OR, remember, is the parallel bar right next to the enter. Now I'm only going to turn on bits if either one is true. So 0, 0, both of those are false. Again, I'm comparing up here, right? I'm comparing these bits for 60 and 13. 60 is represented as binary 0, 0, 1, 1, 1, 1, 0, 0. 13 is represented binary 0, 0, 0, 0, 1, 1, 0, 1. Each one of those numbers represents a bit. So the first bit in 60 is 0, the first bit in 13 is 0. And if I OR those together, 0 and 0, I'm still going to get 0. So that's the first result of the first bit. Second bit, 0, 0 again. Third bit is 1 for 60, and it's 0 for 13. Now, all that means is I have to have 1 true, so that's going to be a 1. Same goes for bit number 4 in 16, 13, so now I have a 1 again. And then a 1 and a 1, they're both true. So again, 1. All I need is 1 true. Another 1. Both false, so that's not going to be true. 0, remember, is not true. 1 is true. And 0, 1, 1. So now I have 0, 0, 1, 1, 1, 1, 0, 1. And the value of that in decimal, if I were to print it out, is again, you have to understand how to convert binary to decimal, but it basically goes 1, 3. I'm trying to add these up, these bits as I go. 1, 3, 7, 15, 30, 61. So this is going to print out 61. End this program and rebuild it, and we're going to see a value of 61. And we do. So that's Bitwise Operators. And again, it's a more kind of advanced for advanced programs, but it's a nice way to represent a lot of data by using ampersands and so forth, by turning on and turning off bits, essentially. So if you didn't, you could play around with this. You could do the exclusive OR, which is the caret, right? The caret is above the 6, number 6 on the keyboard. You would see a different result. If you would add the tilde, that's just going to basically turn everything off. So for A, and A is equal to 60, 0, 0, 1, 1, 1, 1, 0, 0, it's now going to be equal to 1, 1, 0, 0, 0, 0, 1, 1. Right? And if you look at if you convert that binary to decimal, that's then going to be equal to a negative 61. Because remember, this is unsigned, so it can be negative or positive. And the first bit indicates whether or not it's positive or negative. So this has some information to do with binaries. The shifting is kind of cool because if you shift by 2 bytes, so if I say A, shifting you can do with the less than symbols, 2 of them, and I say I want to shift by 2 bytes, all I'm doing is taking the binary number 0, 0, 1, 1, 1, 1, 0, 0 for 60, and I'm shifting to the right. So now the numbers, the 2 zeros in the beginning are going to go at the end. That's shifting to the right. So now I'm going to have basically 1, 1. This is going to be equal to 1, 1, 1, 1, and then 0, 0, and then the 2 first bits are going to be shifted. So 0, 0. And again, if we were to look at the value of that, it would be 240. 1, 3, 7, 15, 30, 60, 120, 240. And then the opposite would be for the shifting to the left. Shift 2 bits to the left. And we could do 3, right? We could do 3. If we did 3 to the left, what we would have here is the first 3 bits would go to the left. So we would have 0, 0, 0. Right? We want to make sure they go to the left, not the right. I'm doing it to the right. So if I A shift to the left, we're going to have 3 bits. We're going to have 1, 0, 0, 0, 1, 1, 1. Wait. 1, 0, 0, 0, 0. I forgot a 0. There we go. 0. Because we're taking this top one and we're going to shift to the left 3. So we're going to say 1, 1. Actually, I messed up. Sorry. 1, 1, 0, 0, 0, 0, 1, 1. There we go. All right. 1, 1, 1. Geez, I keep screwing up. I'm shifting 3. This will be shifting 2. I'm shifting 3, so I say 1, 1, 1. 1, 1, 1, 0, 0, 0, 0, right? 1, 1, 1, 0, 0, 0, 0, 1. Man, see, it can be confusing. You got to watch them. So again, this is shifting to the left 3. So when I go up to 0, 0, 1, 1, 1, 1, 0, I want to shift to the left 3. So my first number is now 1, and then second number is 1, third number is 1, fourth number is 0, 0, and then 0, 0, 1. You wrap them around.